All right, this is a re-recording of Practice Exam 1, Question 1. I had neglected the fact that in the problem that, as stated, the stone, when it hits the surface of the water, loses half of its velocity. This is actually something that makes the problem easier, makes the numbers even simpler. And I had given this problem in some years past. I had not had that feature in, and then when I gave you this problem, I put this feature in, but I'd forgotten that I did that to make the numbers come out easier. And so I gave you the solution to the problem as it was when I gave it a couple years ago. So let's do it again, and now I will get it right. So we have a stone being dropped from a height of 5 meters. And we're supposed to figure out everything about how it moves. So this is split into several parts in the question, right? There's part A of drawing some graphs, and then parts B, C, and D ask you to figure out the maximum depth that it reaches, figure out how long it takes to float back to the surface, and then kind of do a geometrical interpretation. So let's just draw a schematic over here, right? So this is kind of what we expect. If I think of this axis as time and this axis as height, we'll kind of doodle this once schematically and then do it for keeps. Getting out a couple of colors that I'll use to color code different features of the motion. So we expect this to fall down and then float downwards and float back up. And we have to figure out everything about that, how much time these take and the velocity that it hits the surface with, and I mean, we're going to have to work out everything. And it turns out the easiest way to do this is geometrically. So the first thing I want to do is figure out how much time this takes. Turns out everything beyond that's pretty simple. Actually, this is pretty simple too. So we know that x of t is h minus 1/2 gt squared. If I set this to 0, this tells me that t is square root of 2h over g, which tells me that the time it hits the surface, well, this is kind of convenient because height is 5 meters. So 2 times 5 meters is 10 meters divided by 10 meters per second squared is 1 second. So we can fill in the first bits of our graph here. So this means for 1 second, the acceleration is 10 meters per second downward, minus 10. Let me put my minus sign on my axis labels here. And for that 1 second, well, for 1 second, the velocity will decrease from 0 to minus 10 meters per second squared. And, well, we just figured out that this is the position curve doing that, going from 5 down to 0. It's a function whose slope is negative and getting more negative. Remember, the value of the velocity is the slope of the position. So now we move on to the next phase. So now the position here becomes, or excuse me, the velocity here gets cut in half. This is the part that I forgot in my first solution video. So this is cut in half. It becomes 5 meters per second downward. And the acceleration is plus 5 when we are underwater. We don't know how long this goes on for. We'll figure that out. Well, if the upward acceleration is now 5 meters per second every second, and we're at 5 meters per second of velocity, I can fill in this bit, right? In 1 second, my velocity goes from negative 5 meters per second to 0. And when the velocity is 0, this is the deepest point. How deep is that? Well, at this point, we can start labeling some things, labeling the areas in our velocity triangles. So remember, the area of a triangle is 1/2 base times height. 1 second times minus 10 meters per second times 1/2. This is 5 meters, which represents the 5 meters downward that the stone falls in this bit. This triangle, though, is only half as big. It's 5 meters per second height, 1 second base, times 1/2 is 2.5 meters. So this means that the stone goes down another 2.5 meters. .5 meters downward. So we have figured out the deepest point that the stone reaches, 2.5 meters below the surface, because when the velocity is 0, this is the deepest point. And figuring out what happens after that is, well, this curve we expect to be symmetric, right? The curve of rising from the bottom ought to look a lot like the curve to going down to the bottom, right? As this function continues to increase its slope at 5 meters per second every second. So let's continue this. Drew that too far. Right, that's 5 meters per second. And then I've got this triangle whose area is plus 2.5 meters. This is another way to figure out the symmetry, right? That this triangle represents that I'm going 2.5 meters downward, or more further downward. This triangle is 2.5 meters upward, right? Because the area under the velocity versus time curve is the change in position. Let me label this kind of in the same way as all of the others. So this is 2.5 meters downward, is that part. And this then lets us finish the acceleration curve, because we know that it will take 2 more seconds for the stone to get back to the surface. We're underwater for 2 seconds. 1 second on the way down, 1 second on the way back up. So there's the corrected solution for question 1. In a big hurry, right? Really, this is the only equation we wound up needing, because everything else we could figure out geometrically. And this shouldn't be a surprise to you, because this equation, right, the kinematics equations, came from looking at areas under curves to begin with. Let's just label our times just to make things super clear for anyone who's reading this, watching this. This is when the stone hits water at that dotted line at 1 second. At 2 seconds, this is the deepest point. And this time, at 3 seconds, we reach the surface again. So that's the corrected solution to question 1 on the practice exam.